Yeah, I'd like to start with thanking program committee and the organizers for giving me the possibility to present this talk in Toledo. You see here our international team from Moscow State University and from Drake University. And angular distributions, photoelectron angular distributions, a very old topic, of course, so it was developed by years and years. But the advent of new radiation sources, it brings new aspects in this topic. And we listened already yesterday a few talks on the angular distributions, and in my case, and previous talk was also devoted. I will touch only two aspects today. That means, let me check this. I like this more. Yes. I will touch only 2 points. Non-dipole effects in 2-color, XUV plus optical above threshold ionization. Well, already some of you maybe saw a few slides from this part. It was developed a couple of years ago. And then what we call omega plus 2 omega photoionization. I will concentrate on the interference, this 2-path interference between photoionization by fundamental and its second harmonic. Yesterday also was talk on that. And this is really also looks like a very interesting topic, although it's also not new. So then to start with the non-dipole effects in the angular distributions, let us just remind what is the electric dipole approximation. So if this is electromagnetic wave, it's vector potential, and this is interacting charge distribution. If the wavelength is much bigger, much larger than the size of this charge distribution, then we can cut this expansion of the vector potential and stay with this unity, which will give us this electric dipole approximation. Then the second term will give us electric quadrupole and magnetic dipole, and so on. The first correction in the angular distribution, normally in the XUV range, is due to the electric quadrupole amplitude. And this is one example. This is one example only. This is experiment 2003 year, and photoionization from xenon 5s shell, and the energy of the synchrotron radiation only 150 eV. But you see that the actual symmetry with respect to linear polarization of the synchrotron radiation is broken, which indicates the breakdown of the dipole approximation. And also there is forward-backward asymmetry, and somehow to make it, so we just define this differential forward-backward asymmetry like this. So the difference between number of electrons going in this direction and this direction, for example, divided by its sum. And if we integrate photoelectrons in forward and backward hemisphere, then we can end up with this integral forward-backward asymmetry. This is kind of numbers already to be calculated. Okay, how it works? It works due to interference between electric dipole and electric quadrupole amplitudes. So here is the amplitude. This is E1 amplitude, electric dipole, and the Cartesian structure is just Z. So this is cosine theta. If theta is count with from the direction of the linear polarization. So this is just cosine, you see, plus, minus. And the second part can be considered as xz, and this is like this. And if we just sum and take square, well, then plus and minuses, they interfere positively, and you have here this, you know, and here they interfere negatively, and we obtain this type of angular distribution. And this is without interference, you see. Already a long time ago, these formulas have been obtained, and I see also in the audience Professor Musia, who is also one of the pioneers in this theoretical field. So this term just describes you the interference of E1 and E2 photonization amplitude. Okay, this is already well known. And now this is an example, photonization of neon from one S shell. Yeah, and these are these non-dipole parameters. You see gamma and delta. And this is photon energy from the threshold. The threshold is something like 880 or 79 eV. So there are two calculations. So you see that this gamma is rather large. For 3 keV, it can reach 1. And these are the asymmetries. So this is differential asymmetry, 45 degrees, plus 45, minus 45. Yeah? And this is integral asymmetry, so they are smaller. And there were a lot of calculations. But now, okay, so one more illustration. This is the dipole transition, yes, S state, and dipole transition to P state, to P continuum, and this is electric quadrupole from S state to D state, and then these two amplitudes, they interfere. Okay, so this was example for that synchrotron radiation sources. They already made it possible to observe these non-dipole effects in the region of XUV and soft X-rays. From another viewpoint, we have nonlinear optics, which normally is developed in the optical range, and where dipole iodine approximation is well fulfilled. Now we have this X-FELS, and these fields are strong, so we observe nonlinear effects in XUV, but here we have this non-dipole effect, so we have to develop this nonlinear, non-dipole theory of nonlinear processes, including non-dipoles. And this field is not new. Yeah, the topic is not completely new. Yeah, for example, we see here Mark Rakin, our respected chairman, here, and respected second speaker of the session, for example. Yes. So these are few examples of old papers which included this electric quadrupole transitions in the nonlinear calculations. But they were restricted to the cases when there are these resonances between discrete states, so that means that the energies of the photons were quite small. Now we can promote from the beginning electron from the ground state to far into the continuum, and this gives us now a task to develop, for example, for such a process, to develop a theory to include these non-dipole effects due to this big photon. Yeah? So this is 2 photon, 2 color, single ionization. Again, example of neon. That's what I'm talking about now. And let us look how it presents. So such kind of experiments have been done already, but not at such high energies. These experiments at flash already rather long time ago by the group of Michael Meyer. With helium, 90.5 eV. This is X-FEL radiation, and this is optical radiation. And you see the sidebands appear, okay? And you can change mutual polarization of these beams, which is very important, in fact. So, and some theoretical calculations, of course, within the dipole approximation. So these experiments can be done. Now we'll develop a theory, or it has been developed. I'll just present some selected results. For this to color above threshold ionization. So we take these high side bands at the moment, just to be more particular. And we can play with these polarizations, yeah, two linearly polarized lights. And we take collinear beams, okay, two circularly polarized light, etc. Well, we assume that the photon pulses contain many optical cycles and that the photon beams are mutually incoherent. So this is just first step. Therefore, the effects of the pulse shapes, yeah, relative phases of the electromagnetic fields, time delay, are irrelevant in our treatment of the photoelectron angular distributions, and thus the non-dipole contribution to such phenomena as streaking, Carrier envelope phase effects, and other processes for which the time dependence of the electromagnetic field is crucial is beyond the scope of the analysis. This is the first analysis. So it was published recently, and a couple of examples. If we have two circularly polarized beams, okay, the angular distribution is actually symmetric, yeah, and these two circularly polarized beams, they can be either with equal helicities or with opposite helicities, and we have these 5 Legendre polynomials, and the odd ones are just due to this non-dipole contribution. We can subtract one from another and obtain circular dichroisms in the angular distribution, and you see that this term describes us the dipole part, and this describes non-dipole part, and here this cosine, this just gives us forward-backward asymmetry. Now, if we come, for example, for circularly polarized infrared or optical laser and linearly polarized synchrotron radiation, we obtain another formula, of course, and we can, of course, also here distinguish even Legendre polynomials, which are responsible for the dipole part, and odd, which are responsible for the non-dipole part. But we subtract, if we subtract here and find circular dichroism in the angular distribution, then we see that the final expression is pretty simple. So there are only two terms, and the first one is due to the dipole mechanism, and this is non-dipole contribution in the lowest order, of course. We can compare it with what is known, actually. So this was a paper by a French-Russian group of theoreticians. So this was helium, and okay, this is dipole approximation, the same story. If we compare this expression with our first term, we see that they're just identical. If the C is dynamical parameter, so this is product of two amplitudes from two path waves, and their phase difference. But this one gives us some additional term. And what is good, now experimentalists can fit, actually, right? So they know the general how this angular distribution looks, and try to fit the angular distribution. Okay, this is a picture for neon. What I will show further, some examples with neon calculations, and here are these calculations. I just picked up one slide. You see, so these two circularly polarized beams, and we see very big forward-backward asymmetry. This is 3 keV. So yeah, right. And this is the cuts along the plane parallel to the beams. Okay, so you see that they are not symmetric. The solid curves are not symmetric with respect to 90 degrees, and dashed is dipole approximation. Okay. And these are two linearly polarized light with 45 degrees between linear polarization. So you see also such a complicated picture, and again there is some forward-backward asymmetry here. And this is the oops, what? This is an expression for angular distribution when the beams have similar helicity. Sine in the fourth power, and these are two terms, and this one is dipole, and this is non-dipole. You see quadrupole radial integral here, and these are expressions from the second order perturbation theory. And again, if we compare with what was known before, okay, there was a paper by Peter Lambropoulos where he, for the first time, I think, suggested this sine fourth in the fourth power formula, and now we have some additional term due to non-dipole corrections, which again breaks this forward-backward asymmetry. Again, now experimentalists have something to fit to. Okay, a question. Is it possible to make the non-dipole effect stronger in the sidebands than in the main line? The answer is yes, in principle, yes. So this I have shown already. And for example, for 3 kV, this is symmetry here. Okay, it's not bigger than, well, 0.25 maybe, but here you see like 0.5 and so on. I will not stop here on this slide. And so far, the non-dipole effects in the above threshold ionization have not been observed, but looks that modern technique allows to do this. I turn to the second part, which will be shorter, omega plus 2 omega photoionization. What I will consider is, okay, now it's dipole approximation, and this is the two-photon ionization by the photon from, say, X-FEL, and this is its second harmonic, which naturally is presented in the radiation. Its contribution is rather small, but you know, this is the first-order process, and this is the second-order process. And even 1% of the second harmonic, it can dominate over this second-order process. There were already many papers on that done in the optical region, and I think I picked up a couple of examples. There's an interesting analogy with the non-dipole contribution. So you see, this is E1, E2 here interference, and this is interference between these two paths. And these two-photon transitions, they are in a sense look very similar like E2 transitions. The selection rules are very close to each other, very similar. So this is these are transitions E1 plus E2, yeah, and these are these two paths. So in both cases we have two paths, and here 3 paths if it's linear polarization, but there is some analogy here. And how it works in the case of omega to omega interference. Now we can make the same trick. Now the second harmonic is just in cosine. Yeah, it's this one. Yes, and the first harmonic gives us, this is the second order transition. This is z square, and this is this here. Yeah. So and if these two interfere, plus to the left, minus to the right, then it gives us this left-right asymmetry, which has been discussed yesterday also in one of the talks. Yeah, and if we change sign here, then this asymmetry also change sign. So when we change phases between these two harmonics, then this asymmetry, yeah, is controlled. So that is what is called coherent control. So, and you see, despite the fact that the transitions, the rank of the tensors for the E1 and E2 and omega to omega processes look similar, then Cartesian structure is different. And here we have forward-backward asymmetry, and here we have left-right. So it looks interesting. Okay, so this is this definition of left-right asymmetry. Yes, and if we write here 0, then it means really left and right. Yeah, but we can write another angle too. Okay, again, the topic is not new, but it was done in the optical range, not many times, but yes, and this I think was the first in atomic physics. You see, this is again left-right asymmetry as function of phase between the second and harmonic and the fundamental. This was sodium 4s ionization, and in parallel, a few months later, there was PRL independent measurement. This was rubidium. You see these oscillations. So the effect is known. But now we can do it in completely different energy range. And what has not been done so far, as we know, was study of how it looks when there is an intermediate resonance here. So this second order path can be we can make it stronger if we do this resonant to photon ionization. And a couple of slides indeed to show. So this has been done. This was published very recently in the last PhysRef, I think. So this is the field. Yeah, first harmonic, second harmonic, and relative phase. Okay, the individual phases are not important here when the envelope contains many optical cycles. Then this is the case which we consider. Now we have linearly polarized light, and we just take some factor here, which we control, and we can change in theory. That means the weight of the second harmonic. Okay? So, and this is the geometry, and now we are looking for this left-right asymmetry. Okay. So we calculated it for hydrogen, although calculations for neon are in progress. Yeah, first we just wanted to look whether perturbation theory works. So, and this is the population of the 2p state, yeah, for the pulse, for the sine square and with sine square envelope with 40 optical cycles, which is 6 femtosecond on full width and half maximum, and in total it's like 17 femtoseconds. And these are different intensities, yes, and this is the population. Okay, for 10 to 13 peak intensity, we have almost full Rabi oscillation, you know. So of course, perturbation theory doesn't work. It should work when almost all atoms are still in the ground state, you see. So 10 to 11 is okay. Yeah, and here, well, it's questionable, but qualitatively we know that it works now. Okay. So the perturbation theory allows us to write, of course, some analytical equations. I will not comment all the lines here. PT perturbation theory, time-dependent Schrödinger equation, 10 to 12, you understand this is a peak intensity, and we can compare, and this is a symmetry, left-right asymmetry, yeah? Compare these two graphs. This, for example, black one, this one, and black one, this one. And you see that they are really very close to each other. You can, it's red dashed, red dash. So the perturbation theory gives reasonable agreement with brute force and exact calculations here. And these are betas, yeah, beta 1 and beta 3, which are non-zero only when we take into account interference between these two paths. These are these betas which give you left-right asymmetry. Here you see. This is general formula for the angular distribution within the second-order perturbation theory. Okay, and here is this asymmetry. And you see that even betas, as function of phase between the two harmonics, they are constant because there is no interference between harmonics for even betas. And for odd betas, yeah, there is this oscillation. And when we delay one pulse against another one, so the first harmonic and the second, if the delay is 40 cycles, then simply they are not overlapping. Therefore, we don't have any asymmetry, yeah, right? And here is this when they coincide. This is just repeats this curve. Okay, these formulas are not to show you in detail, but what can we do with this, what I considered? You see, we can derive, if the second order perturbation theory works, then we can obtain beautiful equations for the observable quantities, beta 2, beta 4, beta 1, beta 3, asymmetry, and near the resonance, if we consider this resonance as isolated, we also can obtain beautiful formulas, and this 2, it indicates the second order amplitudes into the S channel here, or in the D channel. And 1, where is 1? For example, here, yeah, it indicates P channel. So there are 3 amplitudes, U1, U2D, and US2. And it turns out, so again, these beautiful formulas, it turns out that there is a recipe how to measure partial amplitudes of the first and second order, including relative phases between the amplitudes, that's what normally is meant by complete experiment. And the relative phase between the harmonic we can also measure. And this recipe actually is independent on the relative strength of the harmonics, provided the perturbation theory is valid. It was shown in this paper which I cited. And this is already important because in optics, when you manipulate with lasers, with optical lasers, then you can control the phase and measure it. But in XFEL, this is a problem. You can calculate it, but there is so far as I know, no good recipe how to measure it experimentally. So actually, this is hydrogen, of course, but I'm sure that one can also do it with noble gases too. So this was linear polarization, and I think it's the last slide. For linear polarization, we have left-right asymmetry, okay? But what will happen if we have two circularly polarized beams along one axis? We are used to the fact that when the photoelectron distribution from circularly polarized radiation is actually symmetric, right? And the interesting fact, not well known, is that if we switch to omega plus to omega, this axial symmetry breaks down. So it's maybe difficult to understand when you hear it for the first time. But look, so these are the angular distributions actually for equal helicities and for opposite helicities calculated in the region of the resonance. Anyway, this axial symmetry is broken. And these are the cuts of this angular distribution in the plane perpendicular to the beam. Okay? So you see this, it's indeed broken. Okay. The advent of new radiation sources brings new possibilities to photoelectron angular distribution studies. Why not to use these possibilities? And with this, I'm finishing my talk, and I want to acknowledge many people, actually, so only a few of them are marked here, Giuseppe Sansoni and Kevin Prince and Kiyoshi Ueda and many others for fruitful and illuminating discussions. And with this, I thank you for your attention and have good meals.